Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 787, cheapest flights within K-stops. This is a medium level difficulty graph problem. We're told that there are n cities connected by some number of flights, and we're given an array of flights where flights I is equal to three elements in this list: from, to, and price. So our source, destination, as well as the price. And we're told that we need to find the cheapest price from source to destination with at most k stops. And if there's no such route, we return -1. So in this example, we can go from we have one stop, and it takes us one stop to get to 3 with a price of 700. Now we can, let's assume that, what is it here? N is 4. So, sorry, K is 1. So 1 is the maximum number of stops that we can find as a path. So that's going to be the cheapest result. Now, if we could find a cheaper path, so from, with 2 stops, so 0 to 1, and then 1 to 2, and then 2 to 3, so that's $400 it would cost us with 2 stops, but that would be greater than K, which is the maximum number of stops we're allowed, so we have to return the path which is outlined in red. So how can we solve this problem? Well, we can solve this problem using breadth first search. So create an adjacency list, and then with this adjacency list, we go and find all the different paths and find the path which is cheapest and return that path. Or we can use Dijkstra's algorithm, which is made for a problem like this. And Dijkstra's algorithm will modify it a bit, but it will basically just be breadth first search with a mini heap. That's at its core what Dijkstra's algorithm actually is. But to optimize this problem, we'll also be using a hash map called best, and in best we will store the paths that we've come across so far. And if we find another path that is more expensive than the path in our hash set, then we won't explore that path. We'll prune paths which are not optimal. So let's get into writing our modified Dijkstra's algorithm. So to do that, first of all, I'm going to create our adjacency list. Our adjacency list is going to be equal to a default dictionary, which is going to be a list of lists basically. And we're going to say for flights for flight in flights, for each flight we're going to get what are we told? So source, which is going to be the origin, destination, and the price. And we want to say adjacency list, and remember this is just one directional, so we don't need to do adjacency list both ways. So we just say adjacency list origin, so let's put O in here, dot append, and we want to append the destination as well as the price. So that's our adjacency list created, and now we can actually do breadth first search, using our heap. So in our heap, we're going to push in, we want to order our heap based on, we're going to have a min heap for this, by the way, and we want our first element to be what we sort our min heap by. So we will pass in the price so far. So we'll have in the price, we'll pass in source being the first, our source city, as well as the number of stops. So initially that'll be 0. And we'll also have our best hash set, hash map, whatever you want to call it. And now what we'll say is while heap. So while the heap is not empty, let's get the cost, the city, as well as the cost and the city, as well as the number of stops, which is going to be equal to heap q.heap pop, and we want to pass in heap. So now we're going to have the cost, the city, and the number of stops. And we want to say if the city is equal to the destination city, well then we can just return, what do we need to return? We need to return the cheapest price. So we're going to return the cost that we've got. Otherwise, we now do breadth first search on all the other elements in our graph. So all the other flights. So the first thing we're going to say is we're going to say if the stops is less than or equal to k. So we haven't reached the maximum number of stops so far. I'm going to say for each neighboring city first. So for each next city, and we'll get the price. So we'll get price in adjacency list, and we'll pass in our city. What we want to do is check if the city is in our hash map, and if it is not in our hash map, then we want to then do breadth first search, because it means that we haven't seen this path before, or if it's cheaper than the path that we've visited, then we can explore it. Otherwise, there's no point exploring it. It's just going to be inefficient. So let's say if next city and price is going to be equal to price, or actually no, it's going to be equal to stops plus 1. We're going to say is not in best, and price plus cost, or cost plus price, cost plus price is less than best. Pass in next city, and pass in the price. Okay, we're going to say next city, and the price is going to be equal to, stops plus 1. So in this case, we want to first of all add this path to our hash map so we can check it if we come across another exact path, so then another path to the city with the exact number of stops. So we can just copy paste this, and we're going to set it equal to cost plus price, equal to cost plus price, or cost plus price. Otherwise, what we want to do is add to our heap the new cost and price, the next city, as well as the new number of stops. So let's do that. We're going to say heap q.heap push. The first parameter plus argument is going to be heap, and the second argument is going to be our tuple, which is going to take in just like this. So cost is going to be equal to cost plus price. The city is going to be equal to next city, and the stops is going to be equal to stops plus 1. And that's going to be our breadth first search code done. And then we can just return, like we said, -1 if there is no such route of a cheap flight within k stops. So let's run our code. Let's check if this actually works. And it does not. Let me put you down, because I want to see my code leak. Okay, now we are even more confused. Okay, now where's our test cases? It's up here for some reason. We'll figure it out. City not in best. Key error. Okay. What if, all cost plus price. There should be an or anyway, but I think that's not going to solve our problem. Oh, it does solve our problem. Okay. Okay, that makes sense. So this should have been, we had and here, it should have been or. Let's submit our code. And we pass all 58 test cases. So again, this is a bit of a confusing problem, guys. Once you understand, you need to do a dictionary algorithm, which is, the way I remember it is just a min heap and breadth first search. And then also remember this edge case of we can do it, but we'll get like a time limit exceeded error, because we're just going to be adding too many paths, it's going to be too unoptimal of a solution. So we need to prune paths which we already know we can get to cheaper. And yeah, once you kind of go through the code and nail it in, it does make more sense. So I definitely recommend getting like a piece of paper and just jotting down and kind of walking through the solution based on each, breadth first search iteration, so to speak. But yeah, I hope you guys enjoyed this video, and with that being said, I'll catch you in the next one.